Hello student, welcome to the Web Optics course. Today we have lecture number 63 and we are going to continue the topic birefringent crystal. So today we have lecture number 63 and we will going to continue our discussion on birefringent crystal. And if you remember, in the last class we mentioned that three kind of crystal cutting. For example, here this is one crystal where optic axis is along this direction and three conditions were there. Let me draw once again. And the propagating light was this. So, in the first case, both the component of polarized light is perpendicular to the optic axis OA. However, in other case, one is perpendicular and another is parallel. In this case also one is perpendicular and one is parallel. So, we know that if that is the case, then what happened, that there will be a difference in the refractive index, and these two refractive index corresponds to the two components, and one can have a phase difference out of that. So, the path difference was and the phase difference that one can have for these two components and then so yeah, so this is D. So, that is the phase difference that one can have for this kind of structure. For first case, the there is no effect because both the components are perpendicular to the optic axis. So, there will be no such change, but in other two cases we can have the phase difference, and that is the general form. Now, by adjusting the d, the length of the crystal, it is possible to generate the phase difference as per our desire. For example, if the thickness of the plate is such that, so if the thickness, which is d, if the thickness such that the phase difference is equal to pi by 2, then this whatever the crystal we are talking about should work as a quarter wave plate. Right, or in short, this. In a similar way, one can have also, we can adjust the thickness such that delta phi become pi, then these system, whatever the system, optical system we are talking about, is called the half wave plate. So, also one can have the higher order or thicker quarter wave plate or half wave plate. This is half wave plate by changing the length, and in that case, so for example, higher order or thicker quarter wave plate one can get when delta phi, that is the phase difference between two components, is 2 pi m plus pi by 2. M can be 1, 2, 3, etc. And such optical system in general, so such optical system is in general called that the thing we discuss in our early classes, which is phase retarder. That is, somebody launch, so this is the system, and if we launch a light having these two polarization component, then in the output we will see that there is a relative phase difference between the components. Okay, so there will be relative phase difference between two, and we know that if there is a relative phase difference, then the state of the polarization will going to change. Okay, now what we want to understand something, that is the different kind of crystal, and uniaxial and biaxial crystal to be very precise. So, what is the meaning of that? So, let us define. Before that, we need to understand once again the optic axis that we mentioned. So, the optic axis which we write as OA is corresponds to a, basically it is not a straight line, it corresponds to a general direction corresponds to a direction about which corresponds to a direction about which the atoms are arranged symmetrically. Crystal like those crystals like these for which there is only one such direction, that is the direction along which the arrangement of the atom is symmetric, then they are called uniaxial crystal, uniaxial. Now, if there is one case, now if two such directions are there, then those crystal are called the biaxial crystal. Biaxial. So, the direction of the optic axis inside the crystal determines whether they are uniaxial or biaxial. Several kind of crystal are there. We will show that which shows this kind of characteristics. And what happened if this kind of crystals are there? So, there is a very interesting phenomena that happens for this kind of crystals, and that phenomena is called the double refraction. This is called the double refraction, what happened? For example, we have such crystal, say calcite crystal CO3. Let me draw it nicely. Okay, let me erase this part. Different color, maybe this blue looks bright. Yeah, so we have this point A, this point A prime, this point C, and this point C prime. Along AC prime, we have, say, our optic axis. So this is the direction along which we may have our optic axis. So let me draw the direction of our optic axis. So that means along this direction, the atoms are symmetrically placed. This is our OA. Now, if a unpolarized light is launched here, then one part of the ray which is perpendicular, whose polarized component is perpendicular to OA, will simply follow the usual so this is the state of the polarization. It will follow the regular refraction laws and move along this direction, and this is called the O ray, ordinary ray. However, the other component will start deviating from here and it will go to other direction, and this component is parallel to the direction of the optic axis. Since it is parallel to the optic axis, it will move at different velocity, and that results a deviation from the O ray, and that we call E ray. So this phenomena is in general called the double reflection. This double refraction phenomena we are talking about. So O ray, as I mentioned, let me write. O stands for ordinary ray. And that obeys the usual laws of refraction. So usual law of refraction will be obeyed by this O ray. On the other hand, E ray which is extra ordinary ray, it is in general does not obey general laws of diffraction. Okay, so this is called the double refraction. So one can also understand this with this figure. We will going to discuss this figure in detail, but let me draw it. So what happened? This is a surface, and when O ray fall inside the system, the direction of the light, I mean the velocity of the light is same for all the direction. So that's why it behaves, I mean if I draw the velocity this ellipsoid, so it will be a circle actually. So what happened? So that means I launch a light here perpendicular to the surface, both the cases, and suppose this is the component we are talking about. So what happened when it enters, in all direction the velocity of this component should be same. Now let us have our optic axis like this. So this is the direction of the optic axis. So you can see that the light that was launched, the polarization for that is perpendicular to the optic axis. Then what happened for other polarization is, so the which is parallel to the optic axis, they will move at different speed in different direction. And if I draw an ellipse, it will be something like this. So here this is the point where both ellipse and the circle they touches, because this is the direction of the optic axis. So this particular direction the velocity will same, but what happened that this wavefront, if I draw a so this should touch here, it should not cut, so I need to draw it properly. So that means it should be like this. So it just touch here. So in that case what happened, that the light that is moving will go along this direction. So we have so this is the direction, this dotted line. Let me join it actually. And this is the state of polarization which is parallel to the optic axis. It will move like this and come out from the system in this way. Okay. So, this is the way, I mean, here this is ordinary ray and this is extraordinary ray. This is ordinary ray and this is extraordinary ray. Now, you can see that if a object is placed here in this point, so one, I mean, we can, if I see from this side, we can see the object here as well as if I put these things back here. So, for single object, we can have two refracted, and since the refracted ray for extraordinary is coming in a different path, we can see that the object is basically sitting here as well. And if I rotate that, ordinary ray will, the object that is generated due to ordinary ray will remain fixed, but these things will going to rotate like this way around that. If I rotate the crystal like this. So, that is interesting phenomena, and that I discussed, that happens because the ordinary ray and extraordinary ray, they follow different path. Why they follow different path? Because the optic axis is such that one component is perpendicular, so that is ordinary ray, and another component is parallel. So, this perpendicular or parallel component will move in a different different velocity, and that is why it happens. So, let me note that for uniaxial crystal here, this is one direction along which we have OA, that means optic axis. So, that is why this is a uniaxial crystal. We have NO greater than NE, if that is the case. So, if I write in terms of velocity, so velocity of the ordinary ray will in that case smaller than velocity of the extraordinary ray. So, that means here O ray travels slower at smaller velocity than E ray. So, and this is called the velocity ellipsoid, which suggests that V naught, that is VO, which is represented by this this sphere, and this ellipsoid is defined by VE, which is in that case which is greater than except the direction along optic axis, where both the velocity will travel at same speed. So, this is the phenomena of double refraction. So, in the next class we will continue this point. Today we have much time, we do not have much time. So, in the next class what we do, that we extend this idea and we find out how the ellipsoid, the refractive index is the figure that we draw, how one can obtain this figure, and systematically one can study the light propagation inside those crystals. So, with that note, I like to conclude here. Thank you very much for your attention and see you in the next class.